So I think the time is right now. So I will set my report. Yeah, many thanks for the conveners. My topic is topography media transport of warm deep water across the continental shelf slope in East Antarctic. The ASC is roughly coherent westward current encircling Antarctic and is coupled with the Antarctic slope front, directly influencing the cross-slope heat transport. Sobson et al. 2018 have classified the ASC into 3 different types. First, fresh shelf, second, dense shelf, third, warm shelf. This study focuses on the fresh shelf regions where the ASC and ASLF serve to isolate the cold shelf water from the warm modified circumpolar deep water (MCDW) offshore. However, in the submarine coast and pressed by, warm MCDW is allowed to ventilate the continental shelf in the presence of submarine troughs. Physical mechanisms that govern MCDW intrusion at the submarine trough are the primary focus of our investigation. A variety of mechanisms have been proposed to be responsible for cross-slope exchange. So far, there are already 8 dynamic explanations. However, the dynamic mechanisms that govern the onshore transport within submarine troughs over fresh shelf region are still not clear. We still have 3 questions. First, on the large scale, what drives the onshore flow within the trough? Second, what determines the vertical structure of the onshore flow? Third, how is the temporal variability of the onshore flow? Based on the MIT GCM, we set up an idealized model to represent a typical fresh shelf segment. This system is assumed to be forced by the geostrophic zonal flow corresponding to the ASC. Therefore, the largest scale ASC and ASF are prescribed on the zonal open boundaries by setting the potential temperature theta, the salinity S, and zonal velocity U. Two experiments are conducted. In the control experiment, theta S and U are held constant at the open boundaries. In the season experiment, the theta and S are still held constant, yet a symptotic function is superimposed on U to represent the seasonality of the AIC. Both the control and the season experiments can reach stable state after integration of 2 years. The spatial pattern of theta S at the 500 meter and the barotropical the barotropical serum function are quantitatively in agreement with the observed hydrographic properties over fresh shelf regions. We use 3 meridional cross-section. We use 3 meridional cross-section to preliminarily show how MCW ventilated shelf region in the presence of the trough. Cross-section A, B, C are located at the upstream edge and the mid-trough region, respectively. In the control experiment, at the section A, the relatively high ice hauling can reach shipwreck, yet the coldest isothermal intersects on the upslope. Consequently, the ice picnose associated with MCW is confined to the south of the shipwreck. Such steep ice picnose tilting acts as a potential vorticity barrier that can effectively prevent the MCW from ventilating the shelf region. At cross-section C, the key ice picnose directly extends onto the shelf, and the period barrier vanishes. Warm MCW spreads southward and floods the trough. Over cross-section C, the onshore volume and heat transport across shelf break of the trough shows the temporal evolution of CMCW intrusion. The change in offshore heat transport is currently determined by the onshore volume transport. Significant high-frequency oscillations are also present in the time series, in contrast to the control experiment. The time series from a season experiment exhibited a notable seasonal cycle with a minimum in February and a maximum at the end of March. However, note that the season experiment, the AIC transport prescribed the open boundaries peaks at the end of June. Therefore, it is interesting to find that the seasonality of MCW intrusion is out of phase with the season cycle of AIC. First, we study the force that pushes MCW into the trough. We start from the momentum equation and we can get the full vorticity budget. The vorticity terms are the meridional transport term, as a stretching term, the vacuum term, and the viscosity term. At the zonal cross-section G, the balance of the full vorticity equation is dominated by the stretching term and the vacuum term. By taking an integral of the full vorticity budget equation over depth and scaling with the seawater density, we can have the barotropical vorticity equation. The terms are the direction of geostrophic vorticity, the bottom pressure torque, the direction of relative vorticity, and the curve viscosity. In the eastern flank of trough mouth, the bottom pressure torque play a leading role in the barotropical vorticity balance, mainly counterbalanced by the direction of relative vorticity. Therefore, it's clear that the bottom pressure torque drives the time mean flow. Two profile of the eastern trough mouth shows the vertical structure of the velocity. A striking spatial pattern is characterized by the anti-clockwise rotation of the horizontal velocity vector with increasing depth, referred to as the topography beta spiral. We can substitute the thermal-Venus relation and the continuity equation to the distance balance, and then we can derive the rotation rate of horizontal flow with depth. Since phi z calculated from the analytical equation of the TBS agrees well with the velocity directly from the model output, featuring an anti-clockwise rotation with increasing depth, we can propose that the TBS is expected to be the dominant mechanism governing the vertical structure of the onshore flow. At the M2 station, since the intrusion current has already flowed into the trough, the effects of the TBS are negligible. Next, we try to clarify the high-frequency oscillation in the onshore volume and heat transport over the meridional cross-section H. The Havel diagram of C30 height eta shows that such high-frequency oscillation are associated with the topographic Rossby waves. An analytical solution gives a periodicity of about 4 days for the model configuration. The power spectrum of eta are the three stations S1, S2, and S3 is consistent with the analytical periodicity. In addition, the integral of eta power over the topographic Rossby wave frequency band shows that the energetic region within the trough is located in the northeastern flank. Next, we try to clarify why MCDR in June is out of phase with SC. At the VM1 station, the magnitude of velocity and the prescribed ASC correlate closely. In contrast to the steady increase in U from February to March, the V profile above 400 depths remarkably accelerates. Such suddenly enhanced V in the upper layer is induced by the anti-clockwise rotation of current. The dynamic effects of TBS are expected to be responsible for the maximum onshore transport in March. We calculated the intermediary phi z from February to March as expected. When rho z is reached from the value in February to that in March, the profile of such an intermediary phi z is most close to that in March, confirming the key role of the stratification. So this study aims to clarify 3 dynamic mechanisms responsible for the MCDW intrusion within a trough on a fresh shaft cap. First, the onshore flow is driven by the bottom pressure torque. Second, the vertical structure of the flow is determined by the topographic beta spiral. Third, the high-frequency oscillation of the onshore transport is induced by the topographic Rossby waves. These 3 mechanisms occur simultaneously and govern the MCDW intrusion together. Since the strength of the ASC can regulate the bottom pressure torque, MCW in bottom pressure, MCW intrusion within the trough is expected to covary ASC. However, the maximum onshore transport will lead the strongest ASC by 3 months due to the change of TBS structure in response to the change of the stratification. So thank you for your attention. That's all.
Dr. Kumar, we can hear you.
So I'm sorry, I believe we're having some sort of audio problems here. So let's move on. I don't know, maybe Dr. Kumar. Yeah, so we can hear you yet. So I believe we should move to the next presentation. So maybe I'd like to invite Dr. Klipikov to give his talk.
Okay. Hello, everybody. I will start presentation. Our presentation is instead of first presentation is about some results of monitoring of water mass characteristics in the Antarctic shelf, mainly in the West Antarctic shelf. We, Arctic Antarctic Research Institute, make oceanography studies of the Southern Ocean during the seasonal walks of the Russian Antarctic expedition. Normally, we do sections cross shelf and slope, and also some deep ocean in the vicinity of Russian Antarctic stations. So we have such station in the area of Prud's Bay, Davis-Simoson Sea. It is East Antarctica. But for the last years, several years, we make this station in the Bransfield Strait and in the area of Pacific Ocean near Ruskaya Station. A few words about results obtained in Prud's Bay. We made oceanographic observations in Prud's Bay since 1998, and we made a lot of realizations of section along 70° east, and there is an example of these sections in different years. These sections help us to found the bottom water of which formed in this area. It's we called it Prud's Bay bottom water with a range of temperature minus 0.7 to minus 1.6 Celsius, and with salinity 34,54 to 34,60 practical salinity unit. We also in 2016 we made a survey in the Prud's Bay area with 9 sections with very good resolution, few miles resolution in the area of shelf break, and we obtain quite nice detailed spatial structure of the process of downscaling of shelf water and with bottom water formation. But more detailed presentation on that will make my colleague Mikhail Molchanov, I believe, on at the 8th of August. As I said before, we made oceanographic sections in the West Antarctica. First of all, it's sections at Ruskaya Station. In the Pacific area, this region is very interesting because only few only a few measurements, only a few sections were made in this area in shelf and slope area because of very heavy ice conditions. And also we made several stations in Bransfield Strait and Loper Strait. In Bransfield Strait, it's you see we already made 8 sections, so we can have some comparison and some time realization of temperature and salinity in time. For the sections near Ruskaya station, we found the penetration of the modified circumpolar deep water to the shelf. You see it from these 2 pictures for 2 sections in different areas near Mary Bird Land. And we made 3 sections in 2020, 2021, and 2022, which shows that that there is a decrease in temperature of the bottom layer and not so deep penetration of circumpolar deep water, weakening of circumpolar deep water inflow to the shelf. We obtained for this 3-year realization. For the Bransfield Strait station sections, we made a lot of data since 2016 to 2022. You see the positions of these sections and so main results for the Bransfield Strait, we have 6 repetitions of this section, and we can see that the potential temperature in this area show it warming from -1.8 to -1.58 Celsius, and with some decrease in salinity from 34.6 to 34.56 promiles. Maybe it's some kind of results of global warming in this area, because you know that Antarctic Peninsula, the area to the northern Antarctic Peninsula, one of the area of substantial warming of surface temperature. For the, of course, the area between Ross and Amundsen Sea, area of near Ruskaya station, is poorly provided with observational data, and so it is very important to obtain data for this area. We have only 3 years of realizations of these sections, and we found this circumpolar deep water, modified deep water penetration to the shelf area, and maybe this process could be potential responsible for melting of glaciers in this area. Thank you for your attention.
Thank you, Dr. Klipikov. I'd like to remember everyone that we have this question and answers chat. So I'd like to invite you all to insert the questions there. We're gonna have this questions and answers break after 4 presentations. And we already have a question for Dr. Klipikov, and we'll talk about it later. So I'd like now to invite Dr. Falco, who's going to be talking to us about the study of the freshwater inflow through the eastern gate of the Ross Sea.
Okay, thank you. Can you see my screen?
Yes, perfectly.
Thank you. Okay, sorry. Okay. Okay, in this presentation, I'm going to show you the results we obtained for the analysis of data collected in the eastern sector of the Ross Sea. The data were collected in the framework of the effect of the eastern inflow water on the Ross Sea salinity field variability project, the eastern project. The eastern project was designed to understand the role of waters coming from West Antarctica, which have been considered as the main reason for the decrease in salinity observed in the Ross Sea over the past 50 years. In this slide, you can see a plot where the freshening trend observed in the last 20 years, but the trend is longer and there is evidence of a multi-decadal over 50 years of freshening of the water mass in the Ross Sea, but after the 2014, there has been a sharp increase of the salinity, a recovery of the salinity up to value observed at the beginning of the 90s, as we can see here, for instance, from this curve, which represents the average salinity in Terranova Bay, of the high salinity shelf water, of course, and this rebound was attributed to a climate anomaly that resulted in less ice entering in the Ross Sea from the eastern gate. The multi-decadal trend of freshening was also attributed to the fresh water coming from the eastern, from the West Antarctica. So the eastern gate of the Ross Sea is a very crucial area. And we have to learn much more about this area in order to understand the variability of the salinity field in the Ross Sea. In order to characterize the water mass entering in the Ross Sea, we carry out on the outset summer 2019-2020 an intensive CTD survey centered more or less on Cape Colbeck and along the Ross Sea shelf. The yellow dots here represent the CTD stations where we collect both physical and water samples, which was ultimately used to obtain chemical parameters to describe from a chemical point of view as well the water mass entering into the Ross Sea from the eastern gate. We also deployed the glider. The orange dot represents the glider track. We deployed it for 8 days, and here you can see a zoom in of the track. So the water mass we was looking for is the winter water formed in the Amundsen Sea, characterized by values of temperature salinity in the range indicated here in the slide. So if you look at the vertical section obtained for the easternmost section of our study area and from the vertical section obtained for the westernmost section of our study area represented on the right side of the slide, we can find the Amundsen Sea water, the winter water of the Amundsen Sea region here, more or less limited in this layer, where we can find the same physical characteristic observed in the Amundsen Sea water, in the Amundsen Sea. In the westernmost, and basically we can see in all the section the signal of the Amundsen Sea water. If we move on the westernmost section, we can see that the layer in terms of temperature occupied by the Amundsen Sea water is more or less this one. But if you look at the salinity field, the situation is a bit more complicated because the signal of Amundsen Sea water is almost clear here, but then we have a sharp halocline here, and then there is a strong variation of the salinity, which in some sense is make the identification of the Amundsen Sea water more complicated. So in order to understand better the distribution and what water masses enter from the eastern gate onto the continental shelf of the Ross Sea, we determined the TS diagram on the left side of the slide. There are the TS diagram for all the data collected in the easternmost and westernmost section, whereas here we have the zoom of these two TTS diagram. And as we can see here in the first TTS diagram, we have a clear signal of the Amundsen seawater where the TTS curves change direction, and with a pattern very coherent to what was observed in the Amundsen Sea. Whereas the situation is a bit more complicated in the westernmost section, and but it becomes more clearer if we look at the zoom. So we can see basically the same pattern, the same V-shaped pattern we observed here in the easternmost sector. But as we move toward the Ross Sea shelf, you can see a change of the pattern. The low salinity shelf water appear in the TTS diagram. Also, there is a clear signal of ice shelf water measured in the in the closest station to the Ross ice shelf. It is worth noticing that here the ice shelf water measured here is less salty than the ice shelf water we can observe in the central sector of the Ross Sea. But we use also chemical parameters to describe the Amundsen seawater and all the other water masses. Here in this two bar plot, the mean total alkalinity and mean pH are represented for each water masses we identified, and we can see that there is a clear significant correlation between total alkalinity and pH with the salinity, whereas I did show these results. There is no any correlation with temperature, but considering that the total alkalinity is was traced by a clear value, we can and it is different with respect to the other total alkalinity values measured for the other water mass. We can say that the total alkalinity as well can be considered as a chemical tracer for the Amundsen sea water. So using also, we also determined the trace metal from the water samples we collected in the study area. We determined a lot of trace metals, as you can see here, and we tried to determine the pattern of the Amundsen seawater, describing the variation distribution of the trace metal. For instance, in this map, you can see we joined all the point, all the station where the trace metals was measured and determined in order to create a sort of zonal along the Ross Sea shelf transit. And the distribution of trace metals is very interesting because you can see that there is a strong gradient between the eastern sector and the western sector. This, in some sense, can indicate us that there is no connection between these two points, at least that the water entering through the eastern gate into the Ross Sea is no longer observed here close to the Ross Sea shelf in the western sector of the Ross Sea. But the situation is different if you look at a section obtained or joining all the station along the shelf break. Here we can see that we have a more homogeneous distribution, and the water looks like to follow the Antarctic slope current based on this observation. So if we want to try to give representation of the pattern of the Amundsen seawater in the Ross Sea, we join all the point or the station where the signal of Amundsen seawater is clear. We have a pattern like this with this northern branch, which is basically coherent and parallel to the Antarctic slope current, and the southern branch with this wavy shape that is very likely determined by the change in topography of the area, and then it is determined by, let's say, requirements of the potential vorticity conservation. But we have no indication of any signal of Amundsen seawater along the coast and along the Ross ice shelf as well. So this is basically this could be so concluding we can say that the Amundsen seawater follow mostly the slope current, but it propagates southward but it does not reach the Ross ice shelf. At least as we traced it, we tracked the Amundsen seawater in terms of temperature and salinity, but we also demonstrated that alkalinity can be a good tracer. And also we didn't find any evidence of a coastal branch of Amundsen seawater flow along the Ross ice shelf. In terms of the other water masses, we can say just that based on our data, the circumparative water remained out of the shelf break, and also that we measured a different kind of ice shelf water at about 165 degrees in longitude, characterized this ice shelf water by lower value of salinity. Thank you very much.
Thank you, Dr. Falco, for such an interesting presentation. We still have a few minutes for the next presentation. So I'd like to use this time to just remind you a few tips. And we have this e-poster presentation, which is very interesting. I'd like to invite you all to visit these e-posters. They can be found in the, just a second, in the e-poster exhibition space in the platform. So please just visit those posters. I'll be there. It's really nice. And also, we haven't done this yet, so I'd like to welcome you all to the Southern Ocean Circulation Changes and Consequences parallel session. And we just talked about the questions and answers chat, so please insert the questions there, and we can talk about them later. And finally, this presentation is being recorded, and they will be available at the through the platform. So if anyone has a problem with that, that's no problem. Just email the organizing committee, and the presentation won't be there. But anyway, all presentations should be available through the portal by August 12th, I think, right? So, excuse me, Dr. Alvarino Ruiz, are you available? Maybe could start your presentation already?
Yeah, can I go ahead?
Yeah. Okay, so please, Chuck's yours.
Is the screen visible?
Yes, perfectly.
Okay. Good evening, everyone. This is Luis from National Center for Polar and Ocean Research, Goa, India. And the title of my presentation is Intra-annual Variability of the Hydrological Fronts and Geostrophic Transport between Cape Town and Antarctica during austral summer. Now, I'll give you a brief introduction to the work which we have been doing at NCPOR. Basically, the data that is addressed in this presentation comes from the project Hydrodynamics of the Indian Ocean Sector of Choke Point between Africa and Antarctica, and coastal Antarctica as a part of validation of satellite data. So under this broad theme, we have a couple of objectives, and these are the objectives: monitoring of thermohaline structure, front meandering, and its relation to forcing, with special focus on Antarctic Circumpolar Current. Now, these fronts are, I'm talking about hydrological fronts. Then we have water mass distribution and their mixing characteristics. And third is the monitoring of geostrophic circulation and transport and its temporal variation across the transect between Africa and Antarctica, which I'm going to address in this presentation. And in addition, we install AWS on the cargo ship to validate model-based meteorological parameters. So using this data, the main aim is to study the interannual variability, at the same time to contribute this ocean data to the National Polar Center hosted by NCPOR. So let me give you a brief introduction to the Southwest Indian Ocean sector of the Southern Ocean, why it is important. Now, basically, this is a unique geography with features of bottom topography dictating the Antarctic Circumpolar flow. The bottom features steers the flow and they provide barriers that prevent deep water from mixing except within the deep passages. And among the water masses, we have circumpolar deep water, the most voluminous water mass of the world ocean that is found within the SCC. So in order to do this observations, we deploy XCTD probes, which goes down to about 1,000 meters. And the ships which we are using are chartered for the expedition every year during December to April. So these are not ones that are used for doing oceanography observations, but these are ships that replenish the provision and fuel for the Indian Antarctic stations at Maitri and Bharati. So these are coming to the data that I'm going to address in this presentation. I have 7 tracks that have been occupied during 2007, 9, 13, 14, 15, 16, 17. And most of them were covered during the later period of the austral summer, March, except for 14, it was in April. However, for 2007, it was in December, early austral summer. And these are the distribution of the tracks in between South Africa and Lazarus Sea. Now, what we have done is for the hydrological fronts, we have used traditional definitions that are provided in the literature, and we have used temperature and salinity criteria following Belkin, Gordon, and other host of references here. And volume transport, we have estimated across pair of hydrographic stations computed relative to the deepest common level, that is 1,000 dB, which is the deepest level that is attained for this XCTD probes. And we use a simple equation which is gives the dynamic topography difference between 2 pair of addition stations. And here is the difference. Here is the Coriolis parameter. They have the distance between the 2 stations and the geopotential anomaly between the 2 stations, and we have the depth. So this procedure is as per outlined in Pond and Picard 1983. So coming to the results, we have the hydrological distribution of fronts, temporal distribution from 2007 to 17. What we observe here is that the north subtropical front, which is the branch of the subtropical front, which is northern branch, it spans between 36 to about 39 during 2015 particularly. And what we observe in this particular front is over the period of 7 years that the front is meandering southward. As for the subtropical front, we found a slightly what they call a northward displacement or meandering of this front. For the south tropical front 1, we found a very weak tendency of meandering. However, for subtropical front 2, we found again southward meandering. Continuing, we have the polar front 1, which is again showing a northward meandering, whereas polar front 2 does not have a clear trend. And the south ACC front, we also shows a southward meandering. So these are some typical which we couldn't identify over the period, but the thing is that it is a line section. So it is one point that is we are considering in this particular presentation, in this representation in this figure. Now going to the geostrophic transport. Now here is I have shown in the terms of bars. Now this is since the station distance between 2 stations were varied, because of the logistic reasons. So what I have done is I have computed a transport per half degree width of the latitude. And what I highlight here is the large variation of transport across, for example, polar front 2. We have a particular some years where 2015, for example, with large variability, and 2007 as well. However, for subtropical front 2, we have 2013, we have what you call the positive core, that is the transport from west to east, and the negative represents the transport vice versa, that is from east to west. So higher variability has been found in the mid locations. At the same time, we have for 2007 the coverage. We had a good coverage up to the away from the EZ of Africa, and so we could get the Agulhas front and north subtropical front. And here, because of the Agulhas retrorefraction, we find that we have both types of flow, which is southward as well as the westward flow and eastward flow. So as far as then we try to bifurcate the transport. The total here is the net transport. I say net because we have eastward as well as westward transport. So we sum up, and the transport ranges between 33.5, 34 to about 39, and it shows an increasing trend. And what we found is about 0.87 drops per year. And interestingly, north subtropical front and other front did not show much of a trend. However, for south ACC front, we did find what you call a negative decrease in the transport associated with this front. So the carry home message summary, basically now the discussion part, what I feel is that since the coverage of this station was done within 10 days, so I am of the personal opinion that the maintaining of this fronts as well as the transport modulation is the result of the strong air-sea interaction in that region. And the remote forcing could be the least affected because we are talking about few days, 10 days. So from this analysis of high temporal resolution XCD data, which range from 0 to 100,000 meters, we found that the fronts, north subtropical front SAF2 and south and ACC front exhibited southward meandering, while SSTF, then sub and Antarctic front 1 and polar front showed a northward displacement in their location. Then we found large interannual variability in the geotropic transport, and the total transport shows an increasing trend. So these are some of the findings that I like to share across the audience. And thank you very much for listening to me. That's all.
Thank you, Dr. Overton. So I just another information here. Maybe, I mean, the organizing committee is planning on this presentation is uploaded to our YouTube channel. So that's another place where you can find these presentations. And now scheduled questions and answers break. I just went through the chat and we only have 2 questions there. The first one, Nuncio, was any reason for the CDW intrusion into the shelf in 2020? And Dr. Klepikov said they plan to analyze the atmospheric processes in that year, as well as the ocean circulation in the area, and that now they do not have an answer for that. And maybe I'd like to raise a question here, and that could be to both Dr. Klepikov and maybe Dr. Foucault about what do you think would be the impacts of this, the variability of these intrusions into this shelf of these waters on the formation of the bottom waters, especially the Antarctic bottom water, right? Maybe if you could give us an insight on that, most welcome. Thank you.
Who's that?
You're up, Dr. Falco.
Okay, the production of Antarctic bottom water in the Ross Sea is related now to the two basic water mass. The first is the ice salinity shelf water formed on the continental shelf, and this is influenced by salinity change, of course, in the Ross Sea. So it is some papers, recent paper showed an increase of Antarctic bottom water production from the Ross Sea due to this increase of ice salinity shelf, or the salinity of ice salinity shelf water. So there is a strong impact on the Antarctic bottom water production. That's why we have to pay attention to what happens in the Ross Sea, in the, let's say, at the crucial point where there is this change of waters. This means also through the Eastern Gate, of course, where there is a lack of observation and information that should be fixed in the next future.
Thank you very much. Again, with the you need to analyze as travel dwelling in coastal in the vicinity of is one of the important mechanisms according to CDW. So thank you, Dr. Brindle. We had here for the link to for the Easter session in the chat. So which please just click and you'll be directed to the post session. And I think we don't have any questions so far. So, oh, my voice is a bit fuzzy. Yeah, maybe my connection's best right now. I'm sorry. Yeah, that's the connected world now, right? So I maybe just we won't have problems with later sessions. And we'll be back in 90 minutes, I guess, for Dr. Shu's presentation. Is that all right? All right. Okay, no problem. So, guys, see you again in now 18 minutes. Thank you.
No, you can press it.
This was what off on.
They start video.
This was off on.
Now you can see.
Hi everyone, my name is Yilang Su, and I'm currently a PhD candidate in the MIT Hui Joint Program. My topic is more about small-scale coastal circulation in Antarctica. The title is Influence of Physical Factors on the Stratification Breakdown and then Shelf Water Formation in Antarctica Coastal Plains. Here is the outline of this talk. We have conducted numerical simulations, analytical scaling analysis, and have compiled their results through scientific simulations. As we can see from the left figure, planias are ubiquitous around the coast of Antarctica. But for these coastal planias, they can differ dramatically in terms of their
hello, could you stop?
For the basic,
I think we are on a break right now.
With the diagram on the right. When a strong adiabatic winds blow offshore, the winds slice away, forming a coastal plania. As a result, heat is lost from the ocean to the atmosphere, and sea ice is formed. The dense water from
IT person
and causes strong vertical mixing.
We are currently on a break.
After applying
Could you
water
stop
column
the
mix, the
could you
dense
stop the
water
video?
probably-
Sorry, so we're on a break, and I think we will resume the meeting about 15 minutes later. So could you play the video in about 15 minutes? Thank you.
Oh, thank you. So that's a video. I wasn't understanding anything. So we're on a break. What's going on here? So, okay.
Yeah,
Yeah,
so
please,
I made a
thank you.
pre-recorded video just for the better timing.
Yeah. I mean, that's a good way to go, I guess.
Uh-huh.
Right, just make sure in time. So yeah, we still have I'd say 14 minutes now, and
Okay.
yeah, let's use our break, maybe some coffee. Right, we'll be back.
Okay.
Thank you. If I may, I really like the shirt you're wearing. That is really colorful one in your avatar.
Hi, everyone. I think now we can move on to the next presentation. First, I would like to remember to make your questions to the speakers using the chat box. Now, I think we can play the presentation of Dr. Su.
Yeah, I'm just waiting for the IT person to play the video. I
Yeah.
made a pre-recorded video to better control the timing. And I will
Yeah.
stay for the Q&A session. And yeah, thank you.
IT team, are you here to play the presentation?
Yeah, thanks. Starting now.
Hi everyone, my name is Ilan Su, and I'm currently a PhD candidate in the MIT Rejoin program. My topic is more about small-scale coastal circulation in Antarctica. The title is Influence of Physical Factors on the Stratification Breakdown and then Shelf Water Formation in Antarctica Coastal Plains. Here is the outline of this talk. We have conducted numerical simulations, analytical scaling analysis, and have compiled their results through scientific simulations. As we can see from the left figure, plains are ubiquitous around the coast of Antarctica. But for these coastal plains, they can differ dramatically in terms of their patterns of water column stratification. For the basic planar physics, you are probably familiar with the diagram on the right. When a strong climatic winds blow offshore, the winds can push the sea ice away, forming a coastal plain. As a result, heat is lost from the ocean to the atmosphere, and the sea ice is formed. The dense water from foreign reduction process sinks down and causes strong vertical mixing. After the plain water column is mixed, the dense water can propagate along the bottom and enter the next stage of ABW formation. Therefore, understanding the timing and the magnitude of plain mixing is vital to analyzing their variability in ABW formation in plains. However, here the right diagram only shows the mixing in a 1- or 2-dimensional perspective. But for this talk, I will highlight that plain mixing is actually a 3-dimensional process. Plains has always been an interest in Antarctic research, but there are some gaps in plain studies. For example, coastal plains are poorly resolved in large-scale climate models, and in-situ measurements are hindered by severe winter weather. Also, for realistic numerical simulations, it's difficult to assess the impacts of individual physical factors in complex setups with high uncertainties. Moreover, high resolution is needed to resolve dense water pathways, but this is rarely achieved in realistic models. To resolve these issues, Some previous studies have used idealized numerical or analytical models to understand coastal planar physics. The figure below shows the general setups of the previous idealized models. They prescribe a fixed planar surface with constant surface buoyancy flux, V0. However, this is not what's happening in the real ocean. The winds and sea ice were all absent in these studies. The ocean currents induced by strong climatic winds were neglected in both numerical models and analytical scalings. Here, I'm using the Basins Bay plania as example to show the importance of including winds and sea ice. I have analyzed the wind data at automatic weather stations and find out that both offshore climatic winds and alongshore coastal easterly winds prevail in this region. From satellite images in both figures, we can see that there is an offshore sea ice plume in the Basins Bay plania. This offshore advection of the sea ice is driven by the climatic winds. Under such strong winds, the offshore flow of the sea ice may be accompanied by strong ocean currents in the same direction. Here we assume that the newly formed dense water can also be carried away from the plania by the wind-induced offshore currents, and they do not contribute to local mixing in the planar water column. Hence, if we account for the loss of planar dense water to the offshore region, planar mixing is actually a three-dimensional process. In this study, I used the MIT GCM high-resolution model, and in this model, the ice shelf, sea ice, and the ocean are closely coupled. To test our hypothesis, we have an idealized setup. Here I let winds blow offshore in round B1. The left figure is sea ice area concentration ranging from 0 to 1, and the right figure is the sea ice thickness. We can clearly see the formation of the coastal plania and the offshore sea ice plume. These patterns are similar to what we have seen in the satellite images. We can also take a look at some snapshots of both sea ice and ocean on day 100. Panel A is the sea ice concentration. Panel B is sea ice thickness and ice velocity. Panel C and D are ocean density and current velocity at the surface and the bottom. Panel E and F are passive tracers of the planar dense water at the surface and the bottom. From panel E and F, we can clearly see that the dense water formed on the planar surface is carried away from the plania by the wind-induced offshore currents throughout the water column. And if you look at further south in panel F, some of the dense water sinks down to the bottom and enters the ice shelf cavity. Now we switch to round B2. In this case, alongshore easterly winds are added besides offshore winds. Both sea ice velocity and ocean currents are veering westwards because of the easterly winds. Meanwhile, in panel C and D, higher surface and bottom density is observed in B2 than in B1. This together with panel E and F show that more dense water has penetrated the bottom and entered the ice shelf cavity. After detailed examination of the model results, we realize that the alongshore easterly winds induce onshore aquatic transport, which constrains the dense water outflow. As a result, more dense water stays locally in the planar water column, and vertical mixing is enhanced. Now, for the second part of this study, we have made some updates to the analytical scalings in some previous studies. The pictures are idealized planar water column. B0 is a surface buoyancy flux due to buoyant reduction. Now, we have added the wind effects to the previous analytical work. In our new analytical scaling analysis, the offshore winds BA carry the dense water away from the plania, and this is represented by the lateral density flux V prime rho prime. When alongshore easterly winds UA are present, the aquatic transport in the right figure, QE here, is onshore and constrains the offshore dense water outflow. We can define stratification combination time, STT, which is the time needed to completely break down stratification in the planar water column. I'm not going to the details of the derivation, but essentially, we have included the three-dimensional circulation of the dense water in the formula of STT. The surface production of the dense water, the offshore loss of the dense water induced by the offshore winds, and onshore compensation by the aquatic transport are all included. We can also identify the key physical factors that affect the stratification timescales, and they are listed in this blue box in here. Here, I have performed scientific simulations, and I have compiled the analytically scaled STT and numerically modeled STT. A shorter STT means faster mixing. I want to first highlight the wind effects in panel A and B, since they are very different from the previous studies. In panel A, when the offshore wind speed increases, STT does not change much. This is because when we increase offshore wind speed, the local production of dense water is enhanced due to more heat loss and sea ice production. However, the offshore current is also strengthened and more dense water is carried away from the plania by the ocean currents. This competition between production and loss of dense water weakens the dependence of STT on offshore wind speed. Previous studies neglect the loss of dense water to the offshore region, and in those studies, STT will only decrease with increasing offshore wind speed. In panel B, stronger alongshore easterly winds can also induce stronger onshore economic transport. This process reduces the offshore loss of dense water, and more dense water can stay in the plania water column and enhance local mixing. We have also tested other physical factors, including air temperature, initial ambient radiation, water depth, and wind oscillation period. Overall, the numerical result is consistent with our analytical scaling result. Here's a summary of this talk. First, we have used an idealized numerical model to investigate physical factors affecting water column restratification in planias. Then, analytical scaling formula has been derived to estimate plania destratification timescales. The analytical scaling has been validated against numerical results through scientific simulations. This study addresses the importance of wind effects and shows that the timing and magnitude of plania mixing and dense water transport are affected by wind-induced three-dimensional ocean currents. The numerical and analytical work together provides a framework to estimate the status of stratification in Antarctic coastal planias and can help explain the different patterns of dense water export across various planias. I want to mention another work in progress. We have also investigated how icescape and coastline geometry can affect plania mixing. Here's a case where highland and ice tongue are present. We can see that the dense water circulation and mixing rate have also been changed by these factors. And finally, thank you all for listening. I'd appreciate any questions, and you can always contact me by email.
Thank you, Dr. Su, for your presentation. Now let's move on to the next presentation. The next speaker is Dr. Silvano. Are you ready?
Yes, I'm ready. Can you all see and hear me?
Yes.
Okay, thanks. Okay, I'm Alessandro Silvano from the University of Southampton, and today we'll talk about the decadal variability of ice shelf melting in the Amundsen Sea. This work has been in collaboration with several other scientists from UK, the US, and Australia. Okay, so the Amundsen Sea is very important because this is a map of Antarctic, of mass loss of the Antarctic ice sheet during the past 20 years. And you can see how most of the ice loss has been occurring in the Amundsen Sea embayment. This mass loss is triggered by warm waters, circumpolar deep water from the Southern Ocean that is able to reach the base of the ice shelves in the Amundsen Sea and drive rapid melting. Decadal variability in particular is very important because observations suggest that periods of enhanced retreat of the ice sheet here in the Amundsen Sea embayment are driven by decadal ocean forcing. And so we are really interested in understanding what drives the changes in the decadal variability of melting and forcing. Okay, how this warm water is able to reach the ice shelves. So in the Amundsen Sea, we have warm water in the Southern Ocean called the circumpolar deep water that is transported by the eastward flow near the bottom. This eastward flow is related to the Amundsen undercurrent, which is this eastward current that develops only in the Amundsen Sea, basically. And it's found below a westward surface flow. So we basically have a two-layer system here. Once this eastward undercurrent it's like a canyon is diverted onto the shelf and CDW is transported toward the ice shelves. So changes in the undercurrent causes changes in ice shelf melting in the Amundsen Sea. So here we have been using a model, the MIT GCM, a model run for the past 40 years or so. This map shows the temperature, the background color, and the velocity of the ocean, the vectors, at 450 meters depth, where the circumpolar deep water is located. You can see how you have this eastward flow here, the undercurrent, that is diverted onto the shelf in these canyons. There are three main canyons in the eastern Amundsen Sea. And this is consistent with what we knew from before. If we have a look at the transect across the slope, we can see again this feature of the Amundsen undercurrent. These black lines represent the velocity, solid lines represent eastward flow, and dashed line westward flow. Again, we have this two-layer system with an eastward flow near the bottom. This is again the same map, the same schematic of before. Very important was that despite we have a two-layer system with flow opposite flow at the surface at the bottom, previous work suggested that the variability, the time variability, was barotropic. So basically, when you have westward anomalies at the surface, you also have westward anomalies near the bottom. This is a barotropic response to wind variability. However, what we see in our model is a different response. So we see that at short time scales, you have this barotropic response, but instead at longer time scales, decadal time scales, you have a baroclinic response. So in this time series here, you can see a 5-year running mean of the undercurrent in red and the surface flow in black. So you see how they anti-covary. And also in blue is the ice shelf melting. You can see how it's highly correlated with the undercurrent velocity. We also did a coherence analysis, basically trying to understand the time scales of barotropic and baroclinic response. And when you see this phase angle here around 0, it means that the surface flow and the bottom flow are covariant. So they are positively correlated, but at longer time scales, we see a flip. You have this baroclinic response. So you have that when you have westward anomalies at the surface, you have eastward anomalies at the bottom. With eastward anomalies at the bottom, then you can have increased melting on the ice shelves. So this is what we call a baroclinic response. And why this is important? It's important because it can relate the climate forcing to the ice shelf melting. If we have a look, this is again the same time series shown before. The dashed line here, the black dashed line here, represents the tropical Pacific variability through the triple index. When you have, for example, positive anomalies in the TPI, you can have it's basically representing warmer surface condition in the tropics. And we know that this variability affects the winds in the Amundsen Sea through teleconnections. So what we observe in this model is that cooler conditions in the tropic leads to stronger undercurrent and more melting. This is opposite to what previously we thought. The mechanism, I'm going to go quite quickly here. The mechanism is relatively simple. So we have cooling in the tropical Pacific that drives cyclonic wind anomaly in the Amundsen Sea through teleconnections, atmospheric teleconnections. This represents a deepening of the Amundsen Sea low. These cyclonic winds, these arrows here creates convergence of water near the coast. So the background color is the sea level. So you have convergence of water and sea level rise near the coast. This creates a westward flow at the surface because of the sea level tilt, but it also acts to strengthen the front. So this, the strong front, the Antarctic slope front, which ultimately creates the undercurrent. So you have a steepening of the front, which increases the shear and allows you to have an eastward or a strengthening of the undercurrent. The opposite happens when you have warmer conditions in the tropical Pacific. So cooling in the tropical Pacific in this model suggests that cooling in the tropical Pacific drives more melting in the Amundsen Sea. This is a schematic just to try to summarize this process. When you have cooling in the tropical Pacific, you have an atmospheric cyclonic circulation anomaly in the Amundsen Sea. This is what we call the deepening of the Amundsen Sea low, the low pressure system over the Amundsen Sea. This creates accumulation of seawater near the coast, so sea level rise near the coast, which acts to create a western anomaly in the surface flow because of the sea level tilt, but also act to steepen the isopycnals. This is the baroclinic response typical of the ocean. In this baroclinic response ultimately results in strengthening of the undercurrent, which cause more heat flux onto the shelf and more melting of the ice shelves. So to conclude, previous studies suggested a purely barotropic ocean response to wind variability. Our study suggested this might not be the case at decadal timescales. Our study also suggests that cooler tropical Pacific conditions result in more ice shelf melting in the Amundsen Sea. This is again not previously thought, but of course this is a single model run, and therefore more work is required to confirm it, and also more work is needed to understand the role of other processes such as buoyancy forcing and the detailed mechanisms of the baroclinic adjustment. Just one more slide, if I may, is what are the implications? So we have seen that at decadal timescales we have a baroclinic response. We need to understand if this baroclinic response is also true at longer time scale. So if we think about centennial variability or trends over the 20th century, it's very important to understand whether the ocean had a baroclinic or a barotropic response. This is a reconstruction of sea level pressure in the southern hemisphere and winds over the 20th century, O'Connor et al. You can see two main features. One is the strengthening of the westerly winds due mostly to the anthropogenic forcing over the past century, but also we see a deepening of the Amundsen sea low. So this deepening is potentially linked to natural variability. In case of a purely barotropic response, we would expect just that westerly strengthening of the westerly would cause increase in melting of the ice shelves in Antarctica, in West Antarctica. But in terms of a baroclinic response, instead the deepening of the Amundsen sea low might result in increased melting of the ice shelves. So we have a competition potentially between different forcing, anthropogenic forcing and natural variability. It will be very important to understand which mechanism dominates. At present, we probably don't know. And therefore, the question of whether the mass loss of the West Antarctica sheet during the 20th century is anthropogenic or not is still open, in my opinion. Okay, thank you.
Thank you, Dr. Silvano. And I just would like to remember that the questions will be made at the end of this block of presentation. So the next speaker is Dr. Castaño. Dr. Castaño, you need to unmute your microphone.
Okay, can you hear me now?
Yeah.
Okay, sorry. So today, you can see myself. I think you can see me now. So today I'm going to talk about some of the current observation in the Polinia of the Terranova Bay in the Ross Sea. Why Terranova Bay Polinia? Well, until now we have seen some other presentation talking about the importance of the Polinia, in particular of Terranova Bay. Terranova Bay is one of the area where there is very high production of ice salinity shelf water that is a precursor to Antarctic bottom water, and many studies have focused on the variability of the water properties characteristic, mainly salinity, and how it's changing and what is causing this changing. But very few studies are dedicated have focused on the currents observation. So here today we are going to show some of the some preliminary results of the current observation we have in Terranova Bay from 1995 up to 2022. So where this data came from? This data comes from the Italian marine observed in the Ross Sea. The Italian marine observed in the Ross Sea was started in 2009 to maintain the moorings that were coming from other projects in the past. Now we have 5 active moorings in crucial area of the Weddell Sea. We have mooring D and L that are in the Terra Nova Buipolinia area, where during winter this is the ice in this formation. And we have other moorings, G, B, and HS, that is here, you cannot see here, where we have the export of the Antarctic bottom water from the continental shelf and the import of the circumpolar deep water over the and intrusion of circumpolar deep water over the shelf. So we used in this work the data from mooring D, that is this one, and but before starting to show you some of the results, I want just to show you what's the instrument operations period. So we have a current meter and salinity and temperature sensor since 1995, mostly mechanical current meter in the past, but from 2018, we have only single point acoustic current meters. So we have these instruments at different depth. In the past, there were a little bit of confusion, but from 2010 are mostly at the same depth. So let's see some of the results. Well, first, before going to look at the mooring data, I want to show you some of the, I don't know if you can see this bar. Well, I'm going to show you some of the complexity that we see in the Terra Nova Bay. Well, in the upper part of the slide, you can see a transect close to the Dragaska ice tongue, and you can see that in this transect you have a northwestward current in the western sector of the bay, and a northeastern current on the western sector that is on the left. While if we go a little bit north and then here, and we have a transect of mooring D, mooring D is the triangle here on the bottom, you can see that we have an opposite situation. On the east side of the bay, on the west side of the bay, sorry, we have a northeastward current instead of the northwestward. And on the east side, that is here, this part here, we have a southwestward current. So, but let's look at what we have in the mooring data. The first thing we did a spectral analysis, and from spectral analysis, we can see that the energy peaks are mostly in the tidal and inertial period. The tidal, we have O1 and K1 in the principal lunar declination unisolar, and inertial, that here it's very close to M2, so the M2 component of the tide. But so we have also here a strong tide, I mean, at least in the signal, and the same strong tide we have, for example, close to the shelf break. But let's see what's the strength of the tidal currents. Well, if we do a tidal analysis of the currents, we observe actually that the tides are very weak at all depth. You can see that are very weak at around 500 meters in the intermediate data, very weak at 700 meters, very weak around 1000 meters. This is just for a few years. This is 96-21 and this is 1922, but we see the same thing for all the data we have. From all time series at every depth, we see a very low tide that usually it's weaker than 5% of the total. It's no more than 5% of the total current. So compared to other areas of the Weddell Sea, for example, to the shelf break, the tide here it's very, very weak. For example, at the shelf break in the Dragaski Trough, we have a very high tide. As shown in different papers. For example, Bowen 2021 show how the Antarctic bottom water depends on the tidal on the tidal currents at the shelf break. So what we did after that, we went to check the seasonal signal. What we have in the season. If you see, for example, this on the right, you see the bottom instruments. On the left, you see the intermediate instruments. This is for all time series from 95 to 2022, actually. You can see when we are in summer and spring, we have very low currents, mostly westward, southwestward. While when we are in autumn and winter, we have stronger currents that are mostly directed northeastward. Northeastward, it's direction the Dragaski Trough where mooring is. Why we have stronger currents during winter? Probably we have stronger currents because in winter we have a non-stratified water column. We have a very high salinity and so different density difference between Terranova Bay and the shelf break. And that's the reason we have a strong density gradient, so we have a geostrophic flow. But besides this seasonality, let's go to have some look at what is the typical currents that we observe during the year in Terranova Bay. Well, usually this is just an example, but every year is the same. We have in the bottom layer very northeastward current. You can see from the progressive vector here on the bottom left, it's southwest, and here it's northeast. So the current is going from the bottom left to the upper right. And we can see the same thing in the windrows here, where we have the main direction of the currents towards northeast, in the same direction of the Dagasky Trough. While if you look into the intermediate layer, we see mostly the same. I mean, we have more variability because we are a little bit higher in depth, lower in depth, but still we have mainly the currents that goes northeastward. This is the typical year, but we have an anomaly. We observed an anomaly. The anomaly is in 2021. If you look at the right or the bottom layer, in 2021, we have the currents completely reversed. Now we have the main direction that goes from northwest to south, from northeast to southwest in the bottom layer. Also, this is the bottom layer. We have another instrument at 800 meters that shows the same thing. If we go at 500 meters in the intermediate layer, we can observe there is much more variability, but it's very different from the usual, from the typical currents we observe in the area. Why is that? We don't know yet. We have to explore better this option, but we have few ideas, but we want to understand better what's going on there. So we look at the stick diagram. This is a 14 days filter, and on the bottom layer, intermediate layer, you can see that in the bottom layer on the right, you can see that during 2021 we have a lot of oscillation from northward to southward, while during the other years you have mostly all the currents that go northeastward. The same thing in the intermediate layer. But is this dynamics happening at every depth or just in the bottom and intermediate layer? Well, we observe, if we look at the stick diagram at different depth, this is, for example, 2016, this is 2021, but almost they are all the same, actually. You can see that the current feature that you observe at the intermediate layer and the bottom layer are very similar. You can see the same oscillation at 500 meters, at 1100 meters. The same thing you can see also for 2021, even though it's totally different from other years. So we can say that we have a kind of barotropic flow in Terranova Bay, at least from 500 meters to 1100 meters. So we did a zoom in on Mooring D for just July, August, and you can see also that these data are not filtered, and you can see that there's a lot of oscillation here that are very similar from 500 meters to 1100 meters. But is the surface similar? Well, we went to check some years before 2002, and we looked at 1996, for example, but all other years are the same. And you can observe some features are the same from the tops, from the 140 meters down to from 1000 meters. So, for example, in July, 16 July, that is this one, you can see this variability of the current that is the same throughout the water column. So we can say that this flow in Terranova Bay, it is barotropic. And also we observe an oscillation on 4 or 5 days that we didn't see in the spectral analysis, but we can see this oscillation in the, for example, wavelet analysis. This is 2017-18, but they are all the same. And you can see that this oscillation on 4 or 5 days are mostly during winter. So during winter, we have energy peaks, only during winter. And the periods of this oscillation are about 4 or 5 days, the same that we observed in the currents throughout the water column. So I think I don't have any more time, and that's all. I think we just gave you some of the observation we are looking in Terranova Bay. We hope to have more mooring in the future in the area, because we know that it's just one mooring, but still can give us some interesting information like the barotropic flow we observed in the area. So thank you.
Thank you, Castanho, for your presentation. Now we open for questions. We have a couple of minutes. Would anyone like to send a question to the speakers?
I have a question. So thank you all. Love this presentations. I'd like to know from Dr. Silvano. I understand that it's really hard to separate the anthropogenic sign from the natural variability and all. But I just wonder if you look at those semi-projections for the 21st century, this long-term century scale projections, do you think it could at least get some sort of a way to separate this anthropogenic from the natural variability forcing? Just a guess.
Yeah, so I think there is some work happening, but so in terms of the atmospheric field, okay, so the winds and the sea level pressure, I think it's possible to separate the anthropogenic and the natural variability, especially in the westerly wind bands. In the Amundsen Sea law is a bit tricky, but I think in general there is a good possibility to separate the atmospheric field variability, so to separate the anthropogenic and the natural variability. In the ocean, I don't know. So the models are, I don't know. I think we are a bit far from understanding the long-term variability using models, because you need, especially near the coast, you need a higher resolution to capture these fronts. And so the answer is, I think at present, we don't know the ocean side. In the ocean side is what matters for the West Antarctica ice sheet. So my answer is not super good, but yeah, at the moment we are a bit far. Yeah.
Okay, no, I think it's a very good answer, actually. I think I agree with you 100%. So thank you very much.
Thanks.
We have one more question for Dr. Silvano. This undercurrent that you mentioned in your presentation, it occurs elsewhere and can be expected in other regions such as East Antarctica, and if it doesn't occur in other regions, why only in regions such as Amundsen Sea?
It does occur in other places. So there are observations. The first is from Karen Haywood in the 1990s, and they observed the undercurrent in the Weddell Sea. So they observed this reversal of the flow near the bottom in the eastern Weddell Sea. So it's something that is not only in the Amundsen Sea. It's happening in regions that we call fresh shelves. So where there is a thick layer of fresh water on the shelf. So everywhere there is this kind of situation, you might find an undercurrent. So the Amundsen Sea, the eastern Weddell Sea, potentially the Totten region in East Antarctica. So it's more circumpolar than we thought, I think.
Okay, thank you. I think we don't have any more questions, so I will close the session.
I have a question actually for Dr. Pasquale Castagno. So for the Terra Nova Wave Plania, so I look at the satellite images, so I noticed that the wind direction is to the northeast, and that's very similar to the current velocity you observe, the direction of the current you observe in your moorings. So I'm just wondering, could the climatic winds be the main driver of the current?
Well, I think that down to the bottom, probably not, because we have a we have a strong convection, strong dense water production during winter, and I don't think the wind gets to the bottom. And because when you look at we didn't show, when you look at the surface currents, you see lots of variability related to the winds, because yes, mostly the Katabatin winds there are that direction, but you have lots of winds variability too during the summer, for example, or during winter. But mostly you observe those variability in the surface, but not in the bottom. I think the bottom direction is mostly related to the bathymetry, because you have this trough that is the main axis of the trough is about 55 degrees, so it's a northeastward. But still, we don't understand, for example, why in 2021 the direction is completely the opposite.
I see. But I guess for the intermediate layer, for example, like a couple of hundreds of meters, probably because the wind strength is very strong, probably is still the current maybe still be affected by it.
Yeah, I mean, sure, but it's interesting because what we didn't see, we didn't thought about it, is that also the slide about the fore depth that we have from 140 meters to the bottom, you can see that in the surface sometimes goes everywhere, but there are some of the currents that go the same direction as all the depth. So there is some futures that are barotropic, also at 100 meters. We are going to look more deeply into the other surface currents we have. Unfortunately, they stopped in 2002 because of the iceberg. So we don't put the instruments at that level anymore. But I think that it's very interesting that there is this barotropic characteristic from the surface mostly to go towards the bottom.
I'm also wondering, is your data available on public?
Yes, some of them are already public. So the newest one not already, but we can share the data. We are happy to share the data. So you can just write an email to me, and I can send you the data.
Yeah, because currently I'm trying to do some simulation on a turnover bay, so some kind of validation will be helpful. Yeah,
yes, we are happy to. We are very happy to share the data.
Yeah, thank you.
Thank you. Now I think we don't have more time, so I would like to thank you all speakers and attendees for joining our session, and see you in the next SCAR Open Science Conference.
Thank you.
Thank you, goodbye.
Thank you, everyone.
Thank you.
Thank you. Bye.
Thank you, everyone. See you guys.